viewers, thank you for watching my video. My name is Dr. Venkata. I am working as a professor in the Kumbhalcha Institute of Technology, Volo University, Ethiopia. So today we will discuss a few points related to the Prandtl number. So the Prandtl number is one of the dimensionless number, which is very helpful in the convection heat transfers. So in the convection, there are a few important dimensionless numbers: the Reynolds number, the Prandtl number, Grasho's number, and the Nusselt's number. These are the four important dimensionless numbers we use in the convection heat transfer. So several times you can expect the questions on this dimensionless number. So today we will discuss a few points related to the Prandtl number and its significance. So the Prandtl number, that is the mathematical expression for the Prandtl number is mu Cp by K. Mu Cp by K. This is well known. Mu is the dynamic viscosity. Mu is the dynamic viscosity. The dynamic viscosity of the fluid. Cp is the specific heat of the fluid. K is the thermal conductivity of the fluid. The thermal conductivity of the fluid. So if you know the dynamic viscosity, specific heat and the thermal conductivity of the fluid, these are the properties of the fluid. If you know these, the Prandtl number can be determined. This is a mathematical expression that is well known. How can you define the Prandtl number? Several times such questions you can expect in the competitive examination. The Prandtl number. So the Prandtl number, that is the definition of the kinematic viscosity of the fluid. That is the kinematic viscosity of the fluid, which is connected to the friction. In the denominator, that is taken the thermal diffusivity. The thermal diffusivity. So the ratio of the kinematic viscosity to the thermal diffusivity is called the Prandtl number. So in the numerator, kinematic viscosity, that is related to the friction. The kinematic viscosity, that is also called as the momentum diffusivity. The momentum diffusivity. In the numerator, the momentum diffusivity. In the denominator, the thermal diffusivity. So this is the definition of the Prandtl number. That is the ratio of the momentum diffusivity to the thermal diffusivity. The momentum diffusivity is also called the kinematic viscosity, which has the unit meter square per second. In the denominator, the thermal diffusivity, it has meter square per second. So numerator, denominator, the same units, so both gets cancelled. Then the Prandtl number is become the dimensionless number. So the Prandtl number is the dimensionless number. That is the first point. And how will you get this mathematical expression? The Prandtl number is mu Cp by K. How will you get? So we will substitute numerator, denominator separately. Numerator is the kinematic viscosity. So the kinematic viscosity, it has the definition that is the ratio of the dynamic viscosity to the density. So the ratio of the dynamic viscosity to the density is called the kinematic viscosity, which has the unit meter square per second. This is the another important point for the competitive examinations in view. So the ratio of the dynamic viscosity to the density is called the kinematic viscosity. And the thermal diffusivity. The thermal diffusivity, the mathematical expression for the thermal diffusivity is K by rho Cp. That is the ratio of the thermal conductivity to the product of the density and the specific heat. It is called the thermal diffusivity. So the kinematic viscosity is connected to the friction. The thermal diffusivity, that is related to the heat that can able to diffuse or penetrate into the fluid. So both has the unit meter square per second. Then that is become the dimensionless number. Substitute numerator and denominator in the definition. So the Prandtl number, the numerator is the kinematic viscosity, that is substituted. In the denominator, the thermal diffusivity. that is also substituted. So the density in the numerator and again in the denominator both gets cancelled. Then the Cp is come to the numerator, then the mathematical expression is become mu Cp by K. So the mathematical expression is mu Cp by K and the definition is momentum diffusivity to the thermal diffusivity. So few times such questions are asked in the competitive examination. What is its significance? What is its significance? So if the Prandtl number is less than 1, what happens? So if the Prandtl number is less than 1, means the numerator is less. In the numerator, the kinematic viscosity is less. So the Prandtl number is less, means the numerator is less. In the numerator, either the kinematic viscosity or the momentum diffusivity, that is become less. The kinematic viscosity is less. Viscosity means the resistance offers to the flow. So the resistance is less. So the gases are there. Gases easily can flow. So the flowability of the gases is high. Any gas you can take. Oxygen, carbon, oxygen, nitrogen, otherwise the air, all gases including air. So they have the resistance less. Kinematic viscosity is less. So the Prandtl number is less than 1 for air or gases. If you take the Prandtl number greater than unity, so the Prandtl number is high, the numerator is high. The numerator is high means the momentum diffusivity or the kinematic viscosity. The viscosity is very high. Oil you take. Oil cannot able to move freely. So due to the friction. So the Prandtl number is high means the numerator is high. The numerator is high. The viscosity is high for the oils or water. Oil or water. So for the oil or water, Prandtl number is greater than unity. For the air or gases, the Prandtl number is less than unity. So this is another important point for the competitive examinations. The next point. What is the significance of knowing the Prandtl number? In what way that helps us? So the Prandtl number. So the Prandtl number mainly that is used to find the convection heat transfer. So that is heat due to the convection. So mainly that is used to find the convection heat transfers. So you know the methods to find the convection heat transfers according to the Newton's law of cooling. Q is equal to H into A into the temperature difference. So suppose the fluid is passing over the surface. So the surface has the temperature Ts and the fluid it has the temperature mean stream the temperature. The temperature difference Ts minus the fluid temperature. If you know all these parameters, convection, heat transfer coefficient, the area available for the heat transfer, the temperatures, easily you can determine the convection. If all these factors are known. Suppose if H is not known, how can we determine the convection heat transfer? At the time, few empirical relations will be very useful. So to find H, the convection heat transfer coefficient. So to find H, we require the Nusselt's number. The basic definition, mathematical relation for the Nusselt's number is HL by K. So if you know the Nusselt's number, if you know the dimension of the plate, if you know the thermal conductivity of the fluid, you can determine H. So the H can be determined. So in order to determine the convection heat transfer coefficient, we require the Nusselt's number. So how can you get the Nusselt's number? So the Nusselt's number can be determined using the power law. So the power law that says C times the Reynolds number to the power of m and Prandtl number to the power of n if it is the forced convection. If it is the forced convection, the Nusselt's number can be determined using this relation. So the Prandtl number is useful in this case. Suppose if it is a natural convection means on its own the fluid passes due to the density differences. Suppose if it is the natural convection, the Nusselt's number can be determined the product of the gaseous number and Prandtl number to the power of m. That is for the natural convection. You can see either it is a forced convection or the natural convection. The Prandtl number is essential. If you know the Prandtl number, the Nusselt's number can be determined. Substitute the Nusselt's number, then the convection heat transfer coefficient can be estimated. If you know the convection heat transfer coefficient, then the amount of heat convected can be determined. So, the Prandtl number is highly significant in finding the heat transfers. That is one point. Again, the another. So, in the convections, there are two important points. One is the velocity boundary layer. Another one is the thermal boundary layer. So this Prandtl number is highly significant in finding the boundary layer thickness and again the thermal boundary layer thickness, the relations. So suppose this is the plate. So over the plate, the fluid is passing. So the fluid has a velocity, suppose say mean stream velocity. So this is the plate. This is the surface of the plate. It offers friction. Whenever it offers friction, the fluid particles are moved with a reduced velocity. So very close to the surface, the vicinity will be formed. In this vicinity, the fluid particles passes with the reduced velocity. Once if it crosses the boundary layer, then that gains the velocity of the mainstream fluid. So, the very close to the surface, a vicinity will form. In this vicinity, the fluid particles are occurred with the reduced velocities. This boundary layer, it is called the velocity boundary layer. At any position, so the vertical distance is called the thickness. That is called the velocity boundary layer thickness, which is notated as delta. So it is the velocity boundary layer. Similar to this, the thermal boundary layer also will be produced. That is due to the temperature difference. So the fluid particles are passes with the mean stream temperature. The surface temperature is Ts. So the surface temperature is Ts. The fluid particles, the temperature is the mean stream temperature. So the fluid particles have to pass through this temperature. Very close to the surface, the vicinity will form. So once if the fluid particle passes this vicinity, then the gain the temperature of the mainstream. Within this boundary, the fluid particles are passes with the reduced temperatures. This is called the thermal boundary layer. At the same position, the vertical distance is delta T. That is the thermal boundary layer thickness. This is the velocity boundary layer. This is the thermal boundary layer. How can we relate these? So the thermal boundary layer is the thickness is the ratio of the velocity boundary layer thickness to the Prandtl number to the power of 1 by 3. This is according to the Prandtl mixing theory. So if you know the boundary layer thickness, if you know the Prandtl number, then the thermal boundary layer thickness you can estimate. This is the another significance and which was asked several times in the competitive examination. So these are the few points related to the Prandtl number. So thank you for watching this video.